that I really wanted to talk about was the error formula for Simpson's rule. Okay, so how much error do we get with Simpson's rule? Just like the error with the midpoint and trapezoidal rule, you don't know the actual error, you just know a bound for the error. Okay, so let me tell you what the bound is. It'll feel very similar to the error that we talked about last time. So if you remember the error bounds from yesterday, there was a condition on the second derivative. For Simpson's rule, you have to have a condition on the fourth derivative. Suppose that the absolute value of the fourth, that's a 4, of the fourth derivative is bounded by some constant k. Again, this k is just like it was before. It's a constant that you have to find. Okay. Let me move this up so you can see it. For x in your interval a to b, I'm going to call E sub s the error with using Simpson's rule. Using Simpson's rule. Then this error, the absolute value of ES, it's bounded by K, B minus A. Yesterday it was cubed, but now it's to the fifth over 180 into the fourth. So again, it's kind of a similar formula. There's some differences. The degree of b minus a is now 5 instead of 4, and the degree, your coefficient's different in the denominator, but it's kind of similar-ish. Okay. And the reason why we care, right, about this error bound is because we want to be within a certain margin of error, right? We did a problem involving that, and so let's do one for Simpson's rule as well. Okay. How large should we take n in order to guarantee that Simpson's rule, that the Simpson's rule approximation for, we're still going to use the same integral we've been using all along, the integral from 1 to 2, 1 over x dx is accurate to within 0.001. We saw a question like this yesterday, but for the trapezoidal rule, right? Do you remember what we did?
You guys said the bound for E sub s to 0, 0, 0.
Yep, exactly. So what I'm going to do is I'm going to take this bound here that I have right here in my error approximation, and I'm going to set, so k, b minus a to the fifth over 180 into the fourth, and I want that to be less than 0.0001. Okay? But we've got to find that k value first. I know what b and a are because they correspond to my interval. And I'm trying to solve for n, so the only thing I don't know is what is k. And k, remember, came from a constraint, an upper bound on the fourth derivative. So we're gonna have to take a bunch of derivatives here to figure out what k is, right? So we did, my function was 1 over x, and yesterday we took its derivative. We got negative 1 over x squared. We took a second derivative and got positive 2 over x cubed. So those were all calculations we did yesterday. What's the third derivative? Negative 6 over x to the fourth. And then the fourth derivative, it's going to be a positive 24 over x to the fifth. Okay. Now I want to take this fourth derivative and I want an upper bound for that in my interval. So I'm looking at x between 1 and 2, that's my interval. Take the absolute value of the fourth derivative function. 24, well, hold on. It's positive, like you're telling me, so I can drop the absolute value. And I want to make this number as big as possible, right? So if you plug in 2, right, that's going to give you a smaller number than plugging in 1. Yeah, that's the trick. So here you plug in 1 to get 24 over 1, or just 24, and that's your k value, okay? So this right here is my k value. If x had been in the numerator, then yes, you would have plugged in 2. Okay, so I'm set up, ready to go. I now know k is 24, b is 2, a is 1, and n is what we're trying to solve for. Undo. There we go. Okay, so let's go back to our inequality we had at the beginning. So it was k, 24, b minus 1, 2 minus 1 to the fifth over 180. N is what I'm trying to solve for, so n to the fourth. And I want that to be less than 0.0001. Okay, so that 2 minus 1 becomes a 1, right? 1 to the fifth is just 1. I can simplify this fraction 24 over 180, and I think you're going to get 7.5 when you put that 1 over 7.5. If I remember correctly, you take 180 and divide by 24. I want to solve for n, right? But the n is in the denominator. What do we do? Bring it up to the numerator by multiplying both sides by n over n to the fourth. So you're going to get 1 over 7.5 times n to the fourth. Divide by that decimal so that you've isolated n on the right-hand side. N to the fourth. This 0.00075 And then to solve, you're just gonna take the fourth root of 1 over this decimal. So the fourth root, 1 over 0.00075. This is the part where you would plug it into your calculator to get back a decimal. So what decimal am I gonna get? N needs to be greater than approximately 6.04. So what should I choose N to be? I need it at least as big as 6.04 to be 8, right? Why 8? N has to be even. So there's this little trick with Simpson's rule. You want to just round up, but remember, N has to be even. So you need to pick N to be 8. Again, N must be even. So don't forget that when you're doing Simpson's rule, you need an even number for N.